The Blohm Voss BV 141 is one of World War II's most unconventional aircraft designs, notably distinguished by its striking structural asymmetry. Created by chief designer Dr. Richard Vogt, this German tactical reconnaissance aircraft featured a unique configuration with the crew gondola positioned on the starboard side and the engine mounted on the port side. Despite its radical design that initially drew skepticism from Luftwaffe officials, the BV 141 demonstrated impressive capabilities, reaching speeds of 368 km/h and a service ceiling of 10,000 meters. First taken to the skies on February 25, 1938, the BV 141 was engineered to provide optimal visibility for reconnaissance missions. The aircraft was equipped with multiple 7.92 mm guns and could carry up to 450 kg bombs. However, despite satisfactory performance evaluations and the production of approximately 28 units, including prototypes, the project was officially cancelled on April 4, 1940, giving way to the Focke-Wulf Fw 189. Today, the BV 141 remains remembered as one of the most distinctive aircraft of its time, representing a bold departure from conventional aircraft design principles. Let's explore the unique design of BV 141 in this video. The revolutionary asymmetric design of the BV 141. German aircraft designer Richard Vogt pioneered an unconventional approach to aircraft design with the Blohm Voss BV 141. The aircraft's most striking feature was its asymmetrical configuration, which placed the crew gondola on the starboard side while positioning the engine and main fuselage on the port side. The design of the BV 141 represented a groundbreaking departure from traditional aircraft architecture, embodying a bold and unconventional approach to aeronautical engineering. At the heart of this unique design was the plexiglass glazed crew gondola, which was positioned asymmetrically to the starboard side of the aircraft. This gondola provided seating for the pilot, an observer, and a rear gunner, ensuring that each crew member had an optimal operational environment. On the port side, the fuselage extended in a seamless line from the powerful Beam 132N radial engine to the tail unit, creating a balanced yet highly distinctive appearance. This unusual configuration was not merely an aesthetic choice, but a deliberate design decision aimed at maximizing observational and defensive capabilities. The offset placement of the crew compartment allowed for an unobstructed downward view, enabling the crew to survey the terrain or target areas with exceptional clarity. The lateral field of view was also significantly enhanced, granting the crew a wider visual range and improving situational awareness during missions. Additionally, the layout offered improved coverage for the rear gunner, ensuring more effective defensive operations. The BV 141's innovative design thus blended functionality with creativity, making it one of the most remarkable aircraft of its time. The engineering brilliance behind the BV 141 lay in its careful management of aerodynamic forces. At low airspeeds, the aircraft's stability was maintained through a phenomenon known as P-factor, while at normal flight speeds, the asymmetric forces were effectively controlled through trimming. Furthermore, the tailplane underwent a significant evolution, starting with a symmetrical design before being modified in the 141 billion series to improve the rear gunner's field of fire. Despite early skepticism regarding the aircraft's stability, the BV 141 demonstrated a meticulously engineered balance in its weight distribution. The design team skillfully addressed potential concerns by strategically positioning key components to ensure the center of gravity was precisely maintained. They further optimized the aircraft's performance by achieving an even distribution of lift across the wings, enhancing stability during flight. Additionally, careful attention was given to aligning the thrust line, allowing the aircraft to perform smoothly and effectively despite its unconventional asymmetrical design. The aircraft demonstrated remarkable stability characteristics, reaching a top speed of 248 mph and a service ceiling of 29,530 feet. Additionally, its 700-mile range surpassed its competitors by nearly twofold. When engineers developed the B series, they incorporated the more powerful 1,568 beam 801 engine, necessitating structural reinforcements and size modifications to maintain optimal balance. The asymmetric design presented unique challenges in thrust versus drag management. Consequently, the engineers implemented innovative solutions to counter induced yaw, particularly at varying airspeeds. The placement of the engine on the port side served a dual purpose. It not only provided the necessary thrust, but also helped counteract the P-factor effects during flight operations. Aerodynamic analysis of the BV 141. Modern aerodynamic analysis has revealed fascinating insights into the flight characteristics of the Blohm Voss BV 141. Indeed, this unconventional aircraft demonstrated remarkable stability characteristics that defied initial expectations. Advanced computational fluid dynamics analysis has shown that the BV 141's asymmetric configuration created unique airflow patterns. The offset crew gondola generated distinct pressure distributions, accordingly affecting the aircraft's overall aerodynamic profile. The slipstream effect from the engine was effectively cancelled out by the drag of the cockpit nacelle, which moved the nose rightward. The BV 141 demonstrated remarkable stability in flight, a feat achieved through a series of carefully engineered design elements that addressed the challenges posed by its unconventional asymmetry. One of the primary factors contributing to this stability was the balanced weight distribution between the engine and the offset cockpit sections. The design team meticulously ensured that the mass of these components was proportionally aligned to prevent any undue imbalance that could compromise flight performance. Equally significant was the strategic placement of the aircraft's control surfaces. These elements were positioned to counteract asymmetrical aerodynamic forces, allowing for precise maneuverability and consistent control during various flight conditions. The optimized positioning of the center of gravity also played a crucial role, ensuring that the aircraft's weight was distributed in a manner that supported both stability and responsiveness. Additionally, the thrust line was expertly managed, with the propulsion system carefully aligned to harmonize with the aircraft's unique configuration and aerodynamic requirements. These sophisticated design solutions enabled the BV 141 to maintain stable flight characteristics even at its operational ceiling of 29,530 feet. Furthermore, test flights validated the aircraft's performance capabilities, confirming a respectable top speed of 248 miles per hour. This performance underscored the success of the BV 141's unconventional design, proving not only its feasibility but also its potential as a reliable and effective platform for its intended reconnaissance and observational roles. The asymmetrical configuration of the BV 141 introduced a distinct set of challenges that required innovative engineering solutions. Managing thrusts became a critical concern, as the offset design demanded precise alignment to ensure smooth and efficient propulsion. Similarly, compensating for drag posed a significant obstacle, with the unconventional structure creating imbalances that needed to be meticulously addressed to maintain aerodynamic efficiency. The effectiveness of the control surfaces also required careful consideration, as their placement and operation had to counteract the uneven forces generated by the aircraft's design. Additionally, ensuring stability across a range of speeds proved essential, as the unique configuration could have otherwise led to unpredictable performance under varying flight conditions. A significant advantage emerged from this unusual design. The left-turning tendency from the slipstream effect was naturally neutralized by the cockpit nacelle's drag. Moreover, the aircraft's 700-mile range surpassed its competitors by almost double. The B series introduced several aerodynamic refinements, although these modifications resulted in some operational trade-offs. Rolling became more challenging for the aircraft, whereas its predecessor demonstrated more favorable maneuverability characteristics. The tailplane underwent significant evolution throughout the development process. The initial symmetrical design was modified in the 141 billion series, with the starboard tailplane substantially reduced. Although this modification improved the rear gunner's field of fire, it required careful aerodynamic compensation to maintain stability. Engineering solutions for stability. Maintaining stability in an asymmetric aircraft presented unique engineering challenges for the Blohm Voss BV 141. The engineering team developed innovative solutions to ensure stable flight characteristics through careful balance and control system design. The BV 141's stability was fundamentally reliant on the meticulous management of its center of gravity, which was strategically positioned to the right of the aircraft's geometrical center. This offset placement compensated for the torque and asymmetrical moment generated by the engine and propeller. Engineers achieved this balance by carefully situating the crew gondola on the starboard side and aligning the engine and fuselage along the port side. Additionally, they ensured an even distribution of lift across the wings and strategically managed the placement of fuel storage and equipment to maintain consistent weight distribution. These measures collectively contributed to the aircraft's remarkable stability despite its unconventional design. Advancements in the BV 141's control surfaces further enhanced its performance and operational efficiency. Notably, the tailplane underwent a significant transformation in the 141 billion variant, evolving from a symmetrical configuration to an asymmetrical layout. This modification provided several advantages, including an improved field of view for the rear gunner, enhanced aerodynamic efficiency, better control response at varying speeds, and optimized drag distribution. Similarly, the horizontal stabilizer and elevator adopted asymmetrical designs, ensuring precise control and maintaining the aircraft's maneuverability. The drag created by the offset crew gondola also played a crucial role, naturally counterbalancing the propeller's slipstream-induced left-turning tendency. These innovative design elements underscored the ingenuity and technical sophistication of the BV 141, showcasing the seamless integration of form and function. The flight control systems incorporated several innovative features to maintain stability. At low airspeeds, the P-factor phenomenon largely alleviated stability concerns. Similarly, at normal flight speeds, the aircraft proved easily controllable through trimming adjustments. The control system's effectiveness became particularly evident in managing thrust versus drag asymmetry. Engineers implemented a sophisticated approach where the drag of the fuselage compensated for the tendency to turn left created by the airflow hitting the tail. This solution proved remarkably successful, hence even critics acknowledged the aircraft's exceptional handling characteristics. The BV 141's control systems demonstrated remarkable adaptability across various flight conditions. The aircraft maintained stable flight characteristics through a combination of mechanical and aerodynamic solutions. Ultimately, these engineering innovations enabled the aircraft to achieve controlled flight despite its unconventional configuration, simultaneously proving the viability of asymmetric aircraft design. Structural engineering challenges. The structural engineering of the Blohm Voss BV 141 presented unique challenges due to its unconventional asymmetric configuration. The aircraft's design required innovative solutions to manage uneven load distribution and maintain structural integrity across its distinctive layout. The BV 141's construction primarily utilized sheet balsa for critical components, including wing surfaces and tail assemblies, profile fuselage sections, structural support elements, and joint reinforcement areas. Engineers employed epoxy resin for joining assemblies, ensuring maximum strength with minimal weight addition. Rather than relying on numerous connection points, the design emphasized close-fitting joints with precise epoxy application to maintain structural integrity. The asymmetric configuration of the BV 141 required an intricate and detailed approach to stress analysis to ensure the structural integrity of the aircraft. To prevent potential failure under operational conditions, the engineering team devised a robust method for managing the unique stresses associated with its non-symmetrical cross-section. This process involved pinpointing the precise location of the neutral axis, which served as a critical reference point for understanding load distribution. Effective bending moments were then calculated to determine how forces would act across the structure. The team also conducted thorough analyses of stress distribution patterns to identify areas of potential weakness and ensure that all loads were evenly managed. Finally, they evaluated the sectional properties of the structure to confirm its ability to withstand the complex forces imposed by the unconventional design. The analysis revealed that stress distribution in non-symmetrical sections required careful consideration of both rotational and linear equilibrium at beam ends. Essentially, the team discovered that stresses remained constant through the skin thickness, allowing them to treat the section as a thin line for calculation purposes. The BV-141's structural reinforcement focused on managing asymmetric loads through strategic material placement. The wing center section incorporated a light ply box spar design, enabling selective structural reinforcement in the crew nacelle area. The engineering team utilized one 4-inch triangle stock reinforcement to strengthen critical stress points. The aircraft's unique design necessitated specialized reinforcement in areas experiencing unusual stress patterns. The crew nacelle, constructed from fiberglass, required precise trimming and fitting to maintain structural integrity while providing optimal visibility. The engineering team implemented tab lock construction for self-aligning components, primarily in the wing structure, to ensure consistent load distribution. For managing asymmetric loads, engineers developed a sophisticated system of internal bracing. The structural design incorporated careful consideration of aerodynamic forces, generally resulting in different load magnitudes and directions compared to conventional aircraft. The team addressed these challenges by implementing specialized reinforcement in areas where stress concentrations exceeded normal parameters. Power plant integration. Power plant integration presented unique engineering challenges in the Blohm Voss BV 141's asymmetric design. The first thing to remember, the aircraft's unconventional configuration required innovative solutions for engine mounting and thrust management. The BV-141 was powered by a single beam 801, a 14-cylinder radial engine, capable of producing 1,560 horsepower. Its placement on the port side was carefully chosen to provide multiple advantages. This configuration allowed the engine to deliver maximum power output at sea level, while ensuring an optimal thrust-to-weight ratio for improved performance. The positioning also enhanced aerodynamic efficiency, minimizing drag and maintaining a streamlined profile. Furthermore, the engine's location contributed to strategic weight distribution, naturally counterbalancing the offset crew gondola on the starboard side. With the BIM 801 engine, the BV-141 achieved an impressive top speed of 272 mph and a maximum range of 1,181 miles, demonstrating the effectiveness of its innovative design. The engineering team developed sophisticated solutions for managing asymmetric thrust. As opposed to conventional aircraft designs, the BV-141's engine placement required careful consideration of P-factor effects. The port-side engine mounting effectively counteracted the propeller's natural tendency to create left-turning forces. The thrust management system incorporated several key features, such as strategic engine positioning for optimal thrust line alignment, careful propeller placement for efficient power delivery, advanced control surface integration, and innovative weight distribution solutions. The cooling system design proved crucial for maintaining optimal engine performance. The engineers implemented an air-cooled system that efficiently managed heat dissipation across various flight conditions. The cooling system's effectiveness was demonstrated through several innovative features, including the strategic placement of cooling intakes, optimized airflow channels, an efficient heat exchanger design, and advanced thermal management solutions. The integration of distributed electric propulsion concepts enhanced the overall system efficiency. The power transmission method allowed the combined gas turbine and electric generator to operate at optimal speeds, enabling superior performance across different flight conditions. The engineering team addressed potential cooling challenges by carefully considering thermal load distribution, airflow management, heat dissipation patterns, and system reliability factors. The power plant integration significantly influenced the aircraft's performance envelope. The BIM 801 engine's placement enabled the BV-141 to achieve a service ceiling of 31,810 feet, demonstrating this of its effective unconventional design approach. Crew gondola engineering. The innovative crew gondola of the Blohm Voss BV 141 exemplified the marriage of form and function in aircraft design. This offset compartment, positioned on the starboard side, fundamentally changed how reconnaissance aircraft approached crew visibility and comfort. Visibility optimization was a key focus in the design of the crew gondola, which was equipped with extensive plexiglass glazing and multiple flat panels to provide outstanding observation capabilities. The design featured forward-facing panoramic windows that offered a wide field of view, side-mounted observation panels for lateral monitoring, and an elevated rear gunner position that enhanced situational awareness. Additionally, the gondola provided unobstructed downward viewing angles, ensuring comprehensive coverage in multiple directions. This advanced configuration was further enhanced by the gondola's offset placement, a deliberate design choice aimed at overcoming the visibility constraints typically associated with conventional aircraft structures. By positioning the gondola away from structural obstructions, the observer could maintain clear lines of sight in all critical directions. These innovations collectively provided multi-directional visibility, significantly improving tactical awareness and operational effectiveness in various scenarios. The crew compartment's dimensions were precisely engineered, measuring 3 feet 11.25 inches in width and 4 feet 11 inches in height. The compact design prioritized efficiency without compromising crew comfort or operational effectiveness. The structural integration focused on maintaining optimal weight distribution across the airframe. Engineers designed the gondola to counterbalance the port-mounted engine assembly, essentially creating a harmonious weight distribution that contributed to the aircraft's stability. The crew positions within the gondola were arranged with meticulous planning to ensure functionality and efficiency. The configuration was designed to accommodate 3 crew members: the pilot, situated on the port side of the glazed nose, the observer, stationed on the starboard side, and the rear gunner, positioned in the aft section. Notably, the observer's role was enhanced by an innovative track-mounted seat system, which allowed for seamless movement between different stations. This versatile design enabled the observer to operate the bomb sight from the forward position, access radio equipment at the aft end of the seat track, and maintain optimal positioning to fulfill a variety of mission requirements effectively. The equipment integration included 2 MG-15 machine guns on flexible mounts, providing defensive capabilities. The gondola housed essential navigation instruments, communication systems, and mission-specific equipment. Fundamentally, the layout prioritized ergonomic efficiency, allowing crew members to access all necessary controls and equipment without compromising their primary duties. The rear gunner's position incorporated a Focke-Wulf designed rotating mount, enabling 360-degree coverage. This arrangement maximized defensive capabilities while maintaining the gondola's compact profile. The integration of 4 5 billion bomb racks and an automatic camera system expanded the aircraft's operational versatility. Flight testing and performance. Flight testing of the Blohm Voss BV 141 began with its maiden voyage on February 25, 1938, marking the start of an extensive evaluation program that would ultimately shape the aircraft's development. The development of the aircraft was a meticulous process marked by multiple stages of iteration and refinement. It began with the construction of 3 initial prototypes, which laid the groundwork for further evaluations. These were followed by an evaluation batch of 5 BV 141, a series aircraft, each representing an incremental improvement over the initial design. As the project advanced, significant enhancements were introduced, culminating in the production of the BV 141 billion series, which consisted of 12 aircraft equipped with upgraded BM 801 engines, offering greater power and reliability. Among these, the BV 141 billion 02 emerged as the final evaluation variant, reflecting the culmination of numerous technical advancements. A key figure in the aircraft's development was Ernst Udet, whose personal endorsement provided vital support for the project's continuation. His influence helped drive ongoing refinements, ensuring that each iteration addressed the challenges identified in earlier models. The transition from the A series to the B series marked a pivotal point in the development process, characterized by substantial modifications to the power plant and structural design. These upgrades not only enhanced performance but also demonstrated the project's commitment to innovation and adaptability in the pursuit of an optimized final product. The initial flight evaluations demonstrated promising characteristics. Captain Eric Brown's test flight observations revealed several key aspects of the aircraft's handling. The takeoff demonstrated surprisingly minimal swing, though the undercarriage retraction proved notably slow. At a cruising speed of 325 km/h at 915 meters, the aircraft exhibited stable flight characteristics, fundamentally proving its viability as a reconnaissance platform. The evaluation of the aircraft at Aufklärungsschule 1 during the autumn of 1941 yielded crucial operational insights, contributing to a comprehensive understanding of its performance under real-world conditions. Test pilots reported that the controls demonstrated consistent effectiveness across the entire flight envelope, allowing for reliable maneuverability and precise handling during various phases of operation. However, they also identified areas requiring improvement. Notably, lateral stability exhibited some deficiencies when the aircraft encountered turbulent conditions, suggesting the need for adjustments to enhance its resilience and handling in less favorable weather. Despite this, the landing characteristics were generally described as manageable, indicating that the aircraft maintained a predictable and stable behavior during approach and touchdown. This feature was especially valued for operations requiring frequent landings in varied environments. On the other hand, the hydraulic systems occasionally displayed sluggish behavior, a limitation that pointed to potential inefficiencies in system responsiveness. These findings underscored the importance of addressing mechanical and aerodynamic refinements to optimize the aircraft's overall performance and reliability. The feedback from these evaluations played a significant role in shaping subsequent modifications and design improvements. The BV 141-02 showcased remarkable capabilities across a range of performance parameters, highlighting its advanced design and engineering. It achieved a maximum speed of 368 km/h at sea level, demonstrating its ability to operate effectively at low altitudes. With a service ceiling of 10,000 meters, the aircraft was capable of reaching significant altitudes, offering versatility in mission profiles. Its range extended to 1,900 kilometers, allowing for extended operations without the need for frequent refueling. The structural design balanced strength and efficiency with an empty weight of 4,700 kilograms and a maximum takeoff weight of 6,100 kilograms, reflecting its capacity to carry additional equipment and payloads. Additionally, the aircraft featured a wing loading of 107.75 kg/2, which contributed to its stable flight characteristics and aerodynamic performance. The aircraft achieved a top speed of 438 km/h at 5,000 meters altitude, evidently demonstrating its capability to operate effectively at various altitudes. The power-to-mass ratio of 0.204 kg/kg enabled robust performance across its operational envelope. Primarily, the BV 141's flight testing program revealed both its strengths and limitations. The aircraft exceeded initial requirements in several areas, yet faced challenges regarding engine availability, as the Beam 801 engines were prioritized for the Fw 190 fighter aircraft. The testing phase concluded with mixed results. While the aircraft demonstrated acceptable flight characteristics, external factors ultimately led to its limited production run. Modern engineering assessment. Contemporary engineering analysis has unveiled remarkable insights into the Blohm Voss BV 141's groundbreaking design. Through advanced computational tools and modern validation techniques, engineers have gained a deeper understanding of this asymmetric aircraft's aerodynamic properties. Modern computational fluid dynamics analysis has become instrumental in BV 141's unique characteristics. TranAir, a non-linear full potential solver, enables comprehensive analysis of subsonic, transonic, and supersonic flow patterns around arbitrary configurations. StarCCM, another sophisticated tool, provides finite volume full Reynolds averaged Navier-Stokes solutions for detailed aerodynamic studies. These advanced tools provide a wide range of capabilities, including conducting grid-independent studies for both surface and volume analysis, optimizing domain size to enhance solution accuracy, performing detailed force and moment calculations, and enabling real-time flow visualization. The size of the computational domain plays a critical role in determining the precision of the solution, influencing key aspects of the analysis. Modern approaches prioritize refining surface grids, optimizing volume meshes, implementing accurate boundary conditions, and adhering to rigorous solution convergence criteria to ensure reliable and accurate results. Recent validation studies have unveiled intriguing insights into the BV-141 stability mechanisms. Central to its design was an innovative artificial stability system that utilized two yaw vanes mounted ahead of each aileron. These vanes were directly linked to the ailerons, enabling automatic adjustments to the control surfaces in response to yaw movements, effectively enhancing stability and control during flight. Advanced computational tools have been instrumental in analyzing the aircraft's aerodynamic and performance characteristics. Tran-Air was employed for comprehensive aerodynamic force evaluations across the entire airframe, while STAR-CCM provided detailed insights into localized flow phenomena through flow visualization. Stability analysis was conducted using CCM, which allowed for a thorough examination of the control system's behavior, and performance metrics were validated with DOR F6, which ensured grid independence and accuracy in the computational models. Modern computational analyses have confirmed that the BV-141's asymmetric configuration had minimal impact on critical aerodynamic parameters such as the lift curve slope, minimum drag coefficient, and Oswald efficiency factor. These findings not only validate the ingenuity of the original design, but also affirm the sound engineering principles employed by Richard Vogt and his team, demonstrating the enduring relevance of their work. The BV-141's legacy continues to influence contemporary aircraft design philosophy. Essentially, its unconventional approach demonstrates that asymmetric configurations can achieve stable flight characteristics through careful engineering. The aircraft's design principles have contributed to several modern aviation concepts. The integration of computerized design environments, such as CCM, or computerized environment for aircraft synthesis and integrated optimization methods, enables comprehensive analysis of unconventional configurations. This software suite facilitates mass properties evaluation, adaptive fidelity aerodynamics assessment, linear stability analysis, and control system design optimization. Modern uncertainty and disturbance estimator-based controllers have demonstrated superior performance in managing asymmetric configurations. These advanced control systems effectively compensate for asymmetric disturbances, delivering enhanced trajectory tracking capabilities compared to traditional P controllers. The BV-141's influence extends beyond its historical context. Present-day aerospace engineers utilize its design principles in developing unmanned aerial vehicles and specialized reconnaissance platforms. The aircraft's approach to visibility optimization and structural balance continues to inform modern design decisions. Contemporary analysis tools have validated numerous aspects of the original design. The computational fluid dynamics studies confirm that asymmetric configurations can maintain stable flight characteristics through proper weight distribution and control surface implementation. Furthermore, modern grid independent studies have provided valuable insights into the aerodynamic behavior of offset structures. The application of advanced simulation tools has revealed that the BV-141's design principles remain relevant for modern aircraft development. The integration of computational analysis with physical testing methodologies has established a comprehensive framework for evaluating unconventional configurations. This approach enables designers to explore innovative solutions while maintaining rigorous safety standards. The Blohm Voss BV 141 is a remarkable example of daring engineering during World War II, proving that unconventional designs can achieve impressive stability and performance. Dr. Richard Vogt's team defied traditional symmetrical layouts by focusing on strategic weight distribution, innovative control systems, and advanced structural engineering. Their efforts revolutionized reconnaissance capabilities and demonstrated the potential of asymmetric configurations. Modern computational analyses have validated many of the aircraft's design principles, confirming its aerodynamic effectiveness and lasting influence on unconventional aircraft development. Despite only 28 units being produced, the BV 141 remains an enduring inspiration for engineers exploring bold solutions in aviation. What do you think about the BV 141's asymmetric design? Could such an approach find practical applications in modern aviation? Share your thoughts below.